Now this wouldn't be A-level maths if we couldn't at least use a little bit of vectors with this circular motion. So in the I component, looking at the x direction, we have that the I component is r cos theta in the I direction, and in the y direction, or the j component, we have r sine theta. Now theta can be omega t, and so we get two equations here. So we're going to use the omega t for the purposes of this, because omega is something that we look to calculate and t is something that we look to use. So the first question is here. Okay, so it's defined v with respect to r. So r we had from the basic points of r being r cos omega t in the I component and r sine omega t in the j component. So if we differentiate r with respect to t, we get minus omega r sine omega t in the I component and omega r cos omega t in the j component. So if we calculate the linear speed, we just need to use a bit of Pythagoras, square it, and then combine and square root them. So in doing so, we find that we've got minus r omega r sine omega t squared and omega r cos omega t squared. Now by factorization, we can factorize this omega r squared term out, and then we're just left with sine omega t squared plus cos omega t with a common factor of omega squared r squared. And because sine squared plus cos squared equals 1, that means that that vanishes from the factor. Well, the factorization becomes omega squared r squared 1, which then when you square root it just gives you omega r. So that's quite easy. This second question asks you to compare r and v so as you can look at the angle between them. So I'm going to use the scalar product, but equally you could take the gradient and just say you've got take the gradient and compare the two of them, and you should find that they're at right angles to each other. So the gradient should be minus 1 if you took m dot is equal to minus 1, the gradient product, whatever. So anyway, r dot v, the scalar product, the dot product, r cos omega t I plus r sine omega t j. This is the r component, and then the v minus r omega sine omega t in the I component plus r omega cos omega t j component. We put the I components together and we put the j components together when we take the scalar product, because they're at 90 degrees to each other, the components don't mix. So we're left with r cos omega t multiplied by r omega sine omega t in the I component and sine omega t r sine omega t times by r omega cos omega t in the j component. They stay together. So we're left with an r squared term, an omega, and then cos omega t sine omega t plus r squared omega sine omega t dot cos omega t. So this is a negative, this is a positive, and apart from that they're equal to each other, so they cancel. So when we take the scalar product, we find that we get 0, so r must be perpendicular to v. So what does that tell us about the velocity of the particle? So the velocity is tangential to the circle, or the velocity is at 90 degrees to the radius. Okay. Now this last question looks at acceleration. So to get to acceleration, we just have to differentiate v with respect to t again. So we get minus r omega sine omega t in the I component plus r omega cos omega t in the j component. So that's our velocity. So when we differentiate that, we get minus r omega squared cos omega t minus r omega squared sine omega t. So when we compare that with r, because r was r cos omega t I plus r sine omega t j, we find that we've got a minus omega squared here and a minus omega squared here, and so A is equal to minus omega squared R. Okay, they're identical apart from that minus omega squared component. How do you show that? You show that by factorising this common omega squared term out, and then comparing it with this. Okay, so you substitute R in for R cos omega t in I plus R sin omega tj. So what does that mean? The acceleration is inwards. Okay, the acceleration is negative to the radius or the position. C, calculate the magnitude of A. When you calculate the magnitude, just get A is R omega squared, or just by calculating the magnitude we can do this. The magnitude is just A is R omega squared, because we're now looking at a magnitude. R is no longer a vector because we're looking at the magnitude of it rather than it as a vector. So that's the end of that little section. It's a really useful little section that's basically just some proofs that are useful for using it as a vector. You should be able to do all of those proofs yourself. Okay, hope you found it useful. Bye for now.